In this video, we're going to focus on the three indeterminate powers. Okay, we have 0 raised to 0, infinity raised to 0, and 1 raised to infinity. Again, they are considered to be indeterminate forms because, for instance, let's look at 0 raised to 0. We cannot immediately determine if is it 0, is it 1, is it any other real number, so on and so forth. Okay, and the reason, again, is that this involves limits. Okay, we can actually manipulate these expressions so that we can sort of prove that they are indeed indeterminate forms. Okay, so first thing we need to do is to identify a representation of these expressions. Okay, so we can represent them as an expression raised to an expression because they involve exponentials, right? So we can represent them as expressions or functions raised to another function. Okay, so let's say we have f of x raised to g of x, and then let f of x raised to g of x be equal to, say, another variable, say y. Okay, so we now have a representation of these expressions. F of x raised to g of x can be 0 raised to 0, it can be infinity raised to 0, or it can be 1 raised to infinity. Okay, so next thing we need to do so that we can easily deal with this expression is to bring down the power by using logarithmic functions. So take the natural logarithm both sides of the equation. So we now have ln y equals ln of f of x raised to g of x. And then applying the power property of logarithmic functions, we can bring down the power of the argument and convert it into a coefficient of the ln function, right? So this results to ln y equals g of x ln of f of x. Now let's say f of x raised to g of x is 0 raised to 0. So this will give us g of x, where g of x is 0, ln of f of x, where f of x is 0. Okay, so we have 0 ln of 0, where ln of 0 is negative infinity. So we have 0 times negative infinity. Okay, and if you can still recall, this is an indeterminate product. So it's an indeterminate. Okay. Now let's say f of x raised to g of x is infinity raised to 0. So infinity raised to 0. This will give us, again, g of x ln of f of x, where g of x in this case is 0, and then ln of f of x, where f of x is infinity, so ln of infinity, where ln of infinity is infinity, so 0 times infinity. This is still an indeterminate form. Okay, then lastly, let's say f of x raised to g of x is 1 raised to infinity. So 1 raised to infinity. This time g of x is infinity and then f of x is 1. So we now have g of x, again it's infinity, ln of f of x, where f of x is 1. Okay, so we have infinity, ln of 1 is 0, so that's 0 times infinity. That's still an indeterminate product, so it's an indeterminate. Now let's discuss how to evaluate indeterminate powers. All right, so we'll be applying the same technique that we used here in proving that they are indeterminate forms, specifically this one, taking the natural logarithm of both sides of the equation. Okay, so let's see. Here, of course, we will be given a limit in this form, f of x raised to g of x, and then first step is to equate this limit into, or let this limit be equal to a variable. We usually use n. Okay, and then take the natural logarithm of both sides of the equation. Okay, so ln of n equals ln of the limit of f of x raised to g of x as x approaches a. Okay, and then from here we can interchange these two operations. Okay, ln of the limit of an expression is equal to the limit of the ln of the expression. Okay, and then apply the power property of the ln function. So this will give us ln of n equals limit as x approaches a of the quantity g of x times ln of x. All right, and simplify, apply the limit. The last step is to revert back to n. Okay, isolate n. In other words, we have to eliminate ln so that we can get the original limit. All right, and this is done by applying anti-logarithm. Okay. First problem, we are given the limit of x raised to 1 divided by 1 minus x as x approaches 1. Okay, so let's try to evaluate immediately as x approaches 1. Substitute x equals 1. We have here 1 raised to 1 divided by 1 minus 1. So this gives us 1 raised to 1 over 0. This ratio will approach infinity, so we get 1 raised to infinity. It's one of the indeterminate powers. Okay, so let's apply the technique mentioned or discussed earlier. Let's start by equating the limit, the given limit, to n. Okay, this can be any other variable. All right, we just usually use n, and then take the natural logarithm of both sides of the equation. This will give us ln of n equals ln of the limit as x approaches 1 of x raised to 1 over 1 minus x. Okay, rewrite the equation, apply power property for logarithmic functions. This will give us ln of n equals limit as x approaches 1 of the quantity 1 over 1 minus x times ln of x. Okay, and then let's check if this will give us an indeterminate form. Okay, so we have here 1 over 1 minus x, where x is 1, so 1 minus 1 is 0. Therefore, this ratio will approach infinity. Okay, so 1 over 0, that's infinity. And then ln of 1, because x is 1, so ln of 1 is 0. We have 0 times infinity. That's an indeterminate product. Okay, so it's an indeterminate product. If you can still recall from our previous discussion, if we have an indeterminate product, we have to manipulate it so that we can convert it to either 0 over 0 or infinity over infinity. Okay, so for this equation, for this problem, we can just simply combine ln of x and this factor 1 over 1 minus x, so that we can get this expression, ln of x divided by 1 minus x. And let's check if this will result to 0 over 0 or infinity over infinity, so that we can determine if we can use the L'Hopital's rule, right? So ln of x, where x is 1, again ln of 1 is 0. And then 1 minus x, where x is 1, 1 minus 1, that's 0. So it's an indeterminate quotient. We can now apply L'Hopital's rule. Okay, so applying L'Hopital's rule, derivative of ln of x with respect to x, we have here 1 over x, and then derivative of 1 minus x with respect to x, so that's negative 1. Okay, let's apply the limit. So substitute x equals 1. We now have 1 over 1 all over negative 1. So this gives us ln of n equals negative 1. Okay, and then lastly, we have to eliminate the ln function, because originally we don't have the ln function, right? It's just there to manipulate the original limit. So we have to revert back to n, where n is our original limit. Okay, to do this, we have to apply anti-logarithm. So base of ln functions, base of the natural logarithm is e. So we have to apply this, e raised to ln of n equals e raised to negative 1. Basically, what this does is eliminate the logarithmic function. Okay, and this will give us, on the left side, this will give us n, and then on the right side, that's still e raised to negative 1, or that's 1 over e. This is now our final answer. Okay, next problem, we are asked to find the limit of cosecant x raised to x as x approaches 0. Okay, let's check first by applying direct substitution. So we have here cosecant of 0 raised to 0. Cosecant of 0 is infinity. This is because cosecant is the reciprocal of sine, right? So we have 1 over sine of 0, where sine of 0 is 0. So 1 over 0, that's infinity. Okay. Therefore, we have infinity raised to 0. It is an indeterminate power. So let's try to use L'Hopital's rule. Okay, first, equate the original limit to n, and then apply natural logarithm on both sides of the equation. Next, let's rewrite the equation, apply power property for logarithmic functions. This will result to ln of n equals limit of x ln cosecant x as x approaches 0. Okay, so let's check if this will give us an indeterminate form. Okay, x is 0, so we have 0 ln cosecant of x. Cosecant of 0 again is infinity, ln of infinity is infinity. So we have 0 times infinity, it's an indeterminate product. Okay, so let's manipulate this one so that we can obtain 0 over 0 or infinity over infinity. We can either retain x and then divide it by the reciprocal of ln cosecant x, or retain the more complicated expression, in this case the ln of cosecant x, and then divide it by the reciprocal of x. Okay, so let's try the second option, retaining ln cosecant x and then divide it by the reciprocal of the other factor, which is x, so 1 over x. Okay, so let's try to check if this will give us 0 over 0 or infinity over infinity. Ln cosecant of x, where x is 0. So again, cosecant of 0 is infinity, ln of infinity is infinity. Okay, and then 1 over x, where x is 0. So this ratio will approach infinity, right? So we now have an indeterminate quotient. Let's use L'Hopital's rule. So differentiate the numerator and denominator separately. Derivative of ln cosecant x with respect to x will result to this expression here in the numerator. And then derivative of 1 over x with respect to x is negative 1 over x squared. Okay, so simplifying, we get this one, limit as x approaches 0 of cotangent x divided by 1 over x squared. Alright, this will give us x squared over tangent of x. So we just applied the identity for cotangent x. It's the reciprocal of tangent. And then just transfer x squared to the numerator. Okay, so let's check if this is still an indeterminate form, or indeterminate quotient to be exact. X is 0, so 0. Tangent of 0 is 0, so we still have an indeterminate quotient. So we can still apply L'Hopital's rule. Okay, so applying L'Hopital's rule again, differentiate x squared with respect to x, we get 2x, and then differentiate tangent of x with respect to x, we get secant squared of x. Okay, so let's check. If we apply the limit as x approaches 0, we get 2 times 0. Then on the denominator, we get secant squared of 0. 2 times 0, that's 0. Secant of 0 is 1. 1 squared is 1. So we get 0 over 1, that's 0. And then again, e raised to ln of n equals e raised to 0. On the left side, this will be simplified as n. And then, of course, e raised to 0, any number raised to 0 is 1. So this is now our final answer.